Okay, good evening, everyone, and welcome to our 14th lecture on this series. Topic will be interactions of neutrons with matter. This is actually by request. I'm not an expert in neutrons, neutron interactions, but at least I'm gonna cover some of the basics of these interactions and a little bit on the dosimetry and some comments there. But I mean, definitely there are much more people. There are people who are much more with much more knowledge than me in this topic. Okay. So these are a bit of some of the general aspects probably you're all aware of. So neutrons, they do not have any charge, and they belong to the category of indirect ionizing radiations. Indirect ionizing. It's like photons. Neutrons, they interact mostly with the nuclei. Photons, remember, when we dealt with the interactions, most of the interactions were with the atom or with the orbital electrons. Only I think it's the photonuclear disintegration interaction. That's where a photon interacts with the nucleus directly. And when that happens, then maybe a proton could be emitted neutrons or something can happen there. But when we talk, I mean, with respect to photon interactions, the photon neutron cross-section interactions are very, very small in comparison to cross-sections of photon interacting with the orbital electrons. However, neutrons is the opposite. So neutrons, they interact mostly with the nuclei, actually. And these interactions could be scattering, just simple scattering, whether it's elastic or inelastic. Absorption. So the neutron could be absorbed actually by the nucleus, and then something interesting happens. Or it could be just with very fast neutrons, then we can have just energy transfer to, or it hits the nucleus and when it's smashed, the nucleus just disintegrates and a lot of things could be happening. So spallation, for example, of neutron alpha and so on. Energy is transferred to medium through the heavy charged particles. So it's like any indirect ionizing radiation. So energy transfer to medium is always a two-step process. So with photons, the photons need to transfer first energy to orbital electrons, and then the orbital electrons, they will interact and deposit energy in medium through Coulomb interactions. Again, it's the same thing for neutrons. So neutrons, when they interact, they transfer energy, but the energy will be transferred to heavy charged particles. So this could be protons or even heavier nuclei, and then the protons and the heavier nuclei will interact in the medium through Coulomb interactions to deposit those there. So neutrons, they're classified, one way to classify them is by their kinetic energy. We have ultra cold neutrons. Their energy is very, very small. So it's 10 to the power minus 7 electron volts. And they do have, a speed for these low energies. Their speed is roughly around 6 meters per second. We have very cold, and then we have cold. And then we have the thermal neutrons. These are very important for us. These are neutrons that possess, or they are at actually, let's say, at room temperature. So their kinetic energy is roughly going to be about 0.025 electron volts. And although, I mean, it's a very small energy, the speed of these neutrons is quite high. It's about 2.2 kilometers per second. Imagine that. And then we have higher energy electrons, we have intermediate, and then we have fast neutrons. Those are neutrons with energy greater than 100 keV. their speed in comparison to the speed of light is still about 10 to 15 percent. Okay, remember, speed of light is 3.8, 3.0 times 10 to the power 8 meters per second. A neutron with this, sorry, an electron with this kinetic energy, it's already very close to the speed of light. However, because the neutrons, they're massive, uh, their speed at these energies still much lower in comparison to a fraction of speed, much lower than the speeds of electrons at the same energies. Just to remind you, the mass of or the rest mass energy of neutrons is 939, roughly 939 MeV. And for electrons, it's 0.511 MeV. So the mass of a neutron is roughly around 2,000 times the mass of an electron. So neutron interactions, there are actually 5 interactions that I'm going to cover today. The first one is elastic scattering. Elastic scattering is basically we have a neutron, it hits, for any scattering event, is a neutron interacting with a nuclei. And what happens is that the neutron will lose a bit of its energy, and then it will be deflected at a different angle from its original path. For this type of interactions, then there is going to be some energy transferred to the target nuclei, and one can derive a formula that the mean energy transferred per collision. This is very simple actually to derive. The mean energy transferred per collision is given by this factor here. So for hydrogen, imagine if we had a neutron undergoing elastic scattering with hydrogen. Hydrogen, basically, it's a proton. So the capital M here, this will be the mass of a proton, and mass of proton roughly equals to the mass of a neutron. So when we plug in the numbers here, we will find per collision, the mean energy transfer is going to be the kinetic energy of the neutron divided by 2. So imagine if we have a 1 MeV neutron, and we have a stationary proton, and then the neutron undergoes an elastic scattering. In that interaction, on average, half of the neutron energy will actually be transferred to the proton. Of course, the exact amount of energy will depend on the scattering angle, but if we average over all the possible scattering angles, then we get a mean energy transfer or average energy transfer of 0.5 MeV in this case. So if the neutron had a 1 MeV energy. So if we have a 1 MeV neutron, and we want to actually slow down these electrons so that their energy is at thermal energies, probably they will need to undergo about 25 collisions. 25 collisions would be enough in every collision. So we're going to reduce the neutron energy by 1/2 and so on. This is very useful if you want to do some shielding, shield neutrons, then definitely you would try to select a material that has a lot of hydrogen in it, or low Z material in it, because we know for every interaction of neutrons, the neutrons are going to lose half of their kinetic energy. Although that kinetic energy is going to be transferred to the nucleus, and then let's say for a proton, the proton will have energy, but we know the proton will have a very short range. So for shielding purposes, yes, probably this is the way to go, selecting a low Z material. In comparison, if an electron, if a neutron, and went interacted through elastic scattering with a high Z material, for example, for lead. So at each collision, the neutron will only lose about 1% of its kinetic energy. So here, this equation, we just plug in the mass of lead. Mass of lead, I think we have 209, or so A is 209. So when we plug in the numbers here, we get roughly around 1% only of the neutron energy is going to be transferred to a lead nucleus. So if you want, for example, a 1 MeV neutron to lose its energy until it comes into thermal energy, it will need to undergo roughly around 1,800 collisions. So see the difference? With hydrogen, only 25 collisions are sufficient to reduce the neutron's energy. However, if we had lead, we'll need 1,800 collisions to reduce its energy to thermal neutrons. So this is why if we want shielding, usually low-Z material, or any material that has hydrogen in it, that would be the way to go. We have another interaction. It's inelastic scattering. So basically, with inelastic scattering, this happens with high Z material. And when the neutron energy is more than 10 MeV, then there is a possibility of this happening. So the general form is that we have a nucleus, and then a neutron will, with some energy, will hit this nucleus. The nucleus somehow it moves into a metastable state. A neutron is inside the nucleus with the other nucleons, and then the nucleus then emits a neutron, but with a different energy, with a lower energy probably, plus a gamma. So this gamma photon will also be a byproduct of this inelastic scattering. So an example would be if we had carbon-12, and then it's a neutron undergoes an inelastic scattering with carbon-12. Then at the end, we will get carbon-12. The neutron will be emitted with a lower energy, or be scattered with a lower energy, but then we will have a gamma photon emitted also by the nucleus. So this is probably not a good interaction for shielding, because yes, we're going to reduce the neutron energy, but we're going to get photons, and then we have to deal with photons and shielding and so on. So this interaction has a threshold. For oxygen, it's around 6 MeV, and for high Z material like uranium, it's 1 MeV. Below these energies, this interaction probably will not happen. And then the third interaction, this is a very interesting interaction. This happens with thermal neutrons. So a neutron with this thermal energy is just moving around in matter, and then suddenly a nucleus will grab this, will capture this neutron. So when this happens, these are some of the examples of this interaction. So when this happens, then neutron or the nucleus will become in a different state, and then many things or many possibilities could happen depending on the nucleus itself. So for example, in tissue, hydrogen plus a thermal neutron, we will get a hydrogen, but this is deuterium. So it's a hydrogen plus it's the proton plus the neutron as the hydrogen nucleus, but we will get a gamma photon emitted there. Another example in tissue, nitrogen 14. When it captures a neutron, then we will get carbon 14, and we get a proton. So this is also another possibility of neutron capture. These are very important, when we want to deal with dosimetry of neutrons, let's say biological or in tissue. We want to know the dose to a human and so on. These are probably the most important interactions that one has to deal with. And I will talk about this more later on. In radiotherapy, one particular interaction of interest is the boron neutron capture. And this technique is basically called boron neutron capture therapy. Imagine if we can, by some means, we can actually put boron in the target, in the tumor. And then we bombard or we shower the tumor with neutrons. So what will happen is that the boron will capture these neutrons. And then when it captures the neutrons, we will get lithium-7 plus an alpha particle plus some energy. So the alpha particle, the energy is about 2.7 MeV, if I'm not mistaken. It will be shared by the alpha particle and the lithium ion, I think. And we know that the alpha particles, they do have a very short range. So they can do a lot of damage actually to tissue. So the idea of boron neutron capture therapy is, let's put some boron in the tumor and then shower it with neutrons and let the boron nuclei capture these neutrons. Then we will get these alpha particles, which have a very short range, but they're very damaging. And of course, there are some challenges in this technology that I also will just mention later on. So that's another application of neutron capture. Another application is shielding. So we had cadmium-113 plus a neutron. It will capture it, and it will emit a gamma photon. This is sometimes the way that's used for shielding neutrons is you put some material that has cadmium, and then the cadmium will absorb or will capture the neutrons. But of course, then we'll get gamma photons from that interaction, and then we can surround the material thing with lead in order to shield, or to prevent the lead actually, the photons, from going outside there. So we transfer the neutron into photons, and then we shield the photons. That's the basic idea. And the last example is in radionuclide production. These are three important examples in medical physics. So cobalt-60, we know this is a very important source in radiotherapy. But in nature, we have cobalt-59. We don't have cobalt-60. So what they do is they get cobalt-59, and then they put cobalt-59 in a nuclear reactor. A nuclear reactor, basically, think of it as a sea of neutrons, of thermal neutrons. That's a nuclear reactor. So if we put cobalt-59 there, when it captures a neutron, then it becomes cobalt-60, and a gamma photon is going to be emitted there. So we will do, this is how they put it. They leave it for some time until we get a quantity of cobalt-60 that we want, and then we just take the substance out of the reactor, and there we have cobalt-60. So these gammas, these are actually a byproduct of the capturing process. These are not the gammas of the decay of cobalt-60. Okay, because we know cobalt-60, when it decays, in reality, it undergoes beta decay to nickel-60, and then nickel will immediately emit the two famous gamma photons of cobalt-60. So this gamma is actually not the gammas of the decay of cobalt-60. These are the gamma produced by the neutron capture. Another example, important example, is nuclear medicine, molybdenum. So we know molybdenum is a generator, is used as a generator for technetium-99. So one possible way of generating molybdenum-99 is we get molybdenum-98, we place it inside the reactor, and then it's going to capture the neutrons, and then molybdenum-98 will become molybdenum-99 plus a gamma there from this. Although this is, I think, it's not really the main way of producing molybdenum-99. Molybdenum-99 is produced by another process, which we will talk about. The last one important source is iridium. Iridium-192 is an HDR bracket source used in radiotherapy. But in nature, again, we don't have iridium-192. We have iridium-191 and I think iridium-193. These are the two isotopes of iridium that are found in nature. So if we can get some mass of iridium-191, and then we put it inside the reactor, then the iridium-191 will capture neutrons and become iridium-192 plus some gamma photons. So this is a very important process. Neutron capture has, significant applications, I think, in radiotherapy or in medicine in general. Then we have another interaction is nuclear spallation. So basically, we have a very fast, very energetic neutrons. And what happens? We have a target, and then the neutron hits the target with this energy, and then it defragments the target into smaller particles. So this is an example. We have oxygen-16 and a neutron, very high energy neutron, strikes the oxygen-16 nucleus. Then we get 3 alpha particles, we get 2 protons, and we get two neutrons. Okay. And the last one, this is fission. So fission is basically, it's similar to neutron capture, but the byproduct is a little bit different. So fission happens with very high nuclei, high Z material. And again, these are thermal neutrons. So it captures, the nucleus will capture these neutrons. And then what happens is that once it's captured, then it defragments, it becomes defragmented. It will split into 2, let's say, massive nuclides. And then we get, in addition to that, you get more neutrons. And of course, energy with that. So the amount of energy, this is very simple to calculate. We can look here, for example, we can look at the binding energies of the products and then compare that to the binding energy of uranium. And you will find that actually the binding energies for the products is lower than that for uranium. And the remaining energy or the energy difference, that is actually will be carried out. And that's the energy produced in the interaction. So here is an example, uranium-235. Okay, when this captures a neutron, then a possible byproducts will be krypton, and then we have Ba144, and we get 3 neutrons, or could be, for example, strontium and xenon, for example, and then 2 neutrons. So all of these could happen. And one possibility is we can get molybdenum-99 plus, another relatively large nuclei plus some neutrons. And this is how actually molybdenum is produced in reactors. They bring uranium-235, they bring that plate, and then they put it inside the reactor for whatever time. And all of these interactions will happen inside the uranium plate. Once they leave it for sufficient time, then they remove the plate, and then they will start to chemically separate the radionuclides that are they need. So this should be separated, or it's going to be separated through chemical processing. It's different than production of molybdenum with direct neutron capture from molybdenum-98. And this, obviously, you can see that we have one of the byproducts is actually neutrons. And then these neutrons will go and interact with another uranium nuclide and so on. So this forms a chain reaction. When we when we talked about neutron capture, we see in the byproduct, we don't have neutrons generally for these interactions. And that's why it just happens one time and that's it. But when we're talking about fission, byproducts will have neutrons, and then the neutrons again, they will undergo capturing with another nuclei and so on. And essentially, this is used in nuclear reactors, whether these reactors are used for power, for energy, for electricity production, or for research. Research meaning that production of radioisotopes and so on and so on. So what about the dosimetry now for neutrons? So KERMA, let's look at this is the common term that is used. We need to figure out what's the energy transfer neutrons to charged particles. Remember, we said this is a two-step process. We transfer energy to a charged particle. Then the charged particle, it will deposit the dose in medium, or it's a heavy charged particle. So one of the main differences between neutrons and photons, how it's usually described. Photons, we usually describe them with an energy fluence or an energy flux. So just to remind you, we have an area, and we're looking at the energies or the total energy undergoing through that area. That's the definition of energy fluence. Neutrons, on the other hand, they are often described with the particle fluence. So we count, for example, in that area, how many particles are crossing the area with a specific energy. We're not multiplying it by the energies of the particles. When we multiply the number of particles by their energy, that's the energy fluence. But if we're counting the number of particles just that are crossing the area, that is particle fluence. So neutrons are often described with the particle fluence. So the KERMA in a small mass, if we have a particular interaction and we want to calculate what's the KERMA for that particular interaction, okay, we just need to know how many neutrons are crossing with a specific energy, and then what's the cross-section of that particular interaction. And then we need to just count how many particles, how many nuclei do we have in our volume of interest. And the last factor is, okay, so the interaction happened. What is then the energy transfer to charged particle, or the mean energy transfer to charged particle? So this is, this is basically I think it's very intuitive. So we need to know the fluence will describe how many neutrons are going through our volume. What's the cross-section for that particular interaction? And then how many targets do we have in our volume, or here per mass? So the volume will be defined by our mass. And then for each individual interaction, what is the mean energy transfer? Notice that N over M, so this is the number of targets, nuclei per mass. This is basically Na over A. These two quantities, these are the same. So the mass attenuation coefficient for neutrons is basically the cross-section multiplied by the number of nuclei in our mass M. That's similar to photons, the same thing. So this is the mass attenuation coefficient. But we're going to sum the cross sections for all possible interactions. It's similar to photons. Photons, what did we do? We talked about the cross section for photoelectric, for quantum, Rayleigh, and so on. And then to calculate the mass attenuation coefficient, what did we do? We said, okay, it's the sum of all of these cross sections multiplied by NA over A. So the same thing, N over M is basically NA over A. And we're going to sum over all our interactions, cross sections of these our interactions. So that will give me the mass attenuation coefficient for the neutrons. And the mass energy transfer coefficient, again, we have the mass energy, we have the mass attenuation coefficients for the neutrons, and then we multiply it by the mean energy transfer divided by the energy of the neutron. So this is very similar to photons. Photons, we had the mass attenuation coefficient. We multiplied by the mean energy transfer. This is average over all possible interactions divided by the photon energy. So this is now the neutron energy, and this is the mean energy transfer. If we multiply it by the mass attenuation coefficients of neutron, this gives me the mass energy transfer coefficients for neutrons. So nothing special here. So the total Kerma, again, we will, all what we need to do is just to sum everything over all interactions. And at the end, we get that the Kerma is given by the fluence of, still we're talking about monoenergetic neutrons. So still the beam consists of neutrons with the same energy. So the Kerma will be the transfer coefficient multiplied by their energy, multiplied by their particle fluence. So this is just very similar to I'm just trying to think of photons. So photons, we had here an energy fluence, right? So the EK multiplied by, so this is the energy of the neutrons multiplied by the particle fluence, that will give me the energy fluence. So in photons, the notation was we had the energy fluence multiplied by mu transfer over rho. That's the Kerr definition of photons. But for neutrons, since we like to, or usually the neutrons are described with the particle fluence, then okay, we just need to, the energy should be here. Okay, so we see that term here. So why they do this? Because they define what's called the neutron, and this is Kerr, okay, neutron Kerr factor. And it's basically this product. So this factor here, that is called the neutron Kerr factor. So if you want to know the Kerr, then we just go for that particular energy and medium, because this will also depend on the medium. We get the neutron Kerr factor, and then we multiply it by the particle fluence of our neutrons. And still, this is for monoenergetic neutrons, same energy. And this Kerr will have an SI unit of joules meter squared per kilogram. So the attenuation coefficient, mu transfer over rho, that will have units of meter squared per kilogram, or usually we use centimeter squared per gram, and then we multiply it by the energy, that's the joules there. So the Kerr is therefore given by this, the neutron Kerr factor multiplied by the particle fluence. And here is a chart that shows the neutron Kerr factor for different materials, hydrogen, water, tissue. We have carbon, oxygen, and nitrogen. as a function of the neutron kinetic energy. So this, by contrast, in photon interactions, we will get a plot of the mu transfer, mass energy transfer coefficients. But in neutrons, we get, I mean, the tables are given usually in neutron Kerma factor. So if we have a beam spectrum, not only a single energy of neutrons, then all what we need to do is, okay, let's use that formula and then integrate it over all our neutron energies. So we need to know the fluence for a particular energy, go to the tables and get the neutron form factor, and then move to another neutron. So it's a summation. Essentially, we're doing an integration there. So the dosimetry is very similar to, photons, photon dosimetry, except that, okay, we just need to know the terms, this neutron kernel, things are represented in a different way. But essentially, it's the same thing. Okay, so neutron dose deposition in tissue. So again, neutrons, they will deposit those in tissue through a two-step process. That is something I think now we understand. Why? Because it's an indirectly ionizing radiation. So the first step is let's transfer energy to a heavy charged particle. This could be a proton or even a heavier charged particle. And the next step, these charged particles, then they will deposit the dose through, Coulomb interactions in matter. So let's look at thermal neutron interactions in tissue. We have neutron capture. Remember at the table there, here we're looking at these two interactions, neutron capture. So with nitrogen 14, we have nitrogen 14 plus neutron. So this is the capture. We get carbon 14 plus a proton. The cross-section for this interaction is about 1.8 bars per atom. And the energy transfer per interaction is 0.63. This is very simple to calculate. Neutrons, essentially their kinetic energy is zero. They don't have any binding energy, and so on. So what we need to do is we need to calculate the binding energy of nitrogen 14, or from the tables, we can get the data from the tables of the binding energy. And then we look at the binding energy for carbon 14. And once we do this, you will see that if we subtract, the difference is going to be 0.63 MeV. And that is basically the energy available to these two particles. Since carbon is much more massive than a proton, then the assumption is that this proton will actually grab or will take all of this available energy. So when this interaction happens, the protons will be produced with a kinetic energy of 0.63 MeV. And then the Kerma per unit thermal fluence, if we go and get the F factor, go all of this data, and the Kerma per neutron fluence is about 2.4 10 to the power minus 17 grays meter squared per neutron. For hydrogen, it's again the same thing, but there is something different here. So with hydrogen, when neutron captures hydrogen, we get a deuterium, but we don't get actually a charged particle. We get a gamma. So imagine if we had a very small mass, we're talking about tissue, a small body, then essentially these gammas, they will come out with an energy of 2.2 MeV. Again, we can calculate it just using the binding energies. And this is the cross-section of the interaction. So these gammas will have an energy of 2.2 MeV if our volume is very, very small. Then, of course, the assumption is that these gammas are going to escape. So actually, no dose probably will be deposited there. On the other hand, if our volume is really large, then these gammas, they will interact. The assumption is that they will be absorbed somewhere in that body or that mass. And so when this interaction happens, we don't have an energy transfer because we have a gamma here. But what we can do is we can, actually, this should be an energy, it's not kernel. We could then say, okay, what is the energy transferred to gammas per fluence per mass? Okay. So just so this is energy per mass, and here is Kerma. Kerma is energy per mass. So we need to split. We're now looking at the energy of the gammas divided by the particle fluence divided by the mass. This is roughly around 7.7 times 10 to the power minus 16 grays per meter. So the point I'm showing this is that actually when a neutron is captured by nitrogen, we get actually higher energy, we get more energy deposited in the body per neutron fluence. That's important that we have to, because now I'm going to twist this. So if this interaction happens, then this is the energy that is going to be deposited per neutron. Now, if this interaction happens, and let's assume that the photon will interact in the body, it's not escape, then actually the energy is lower than this. Okay, the energy deposited in tissue is like this. Okay, per neutron. So I'm still emphasizing it's per neutron. So this is the human tissue composition. If we look at hydrogen, 10%, carbon, 70, this 75, I think, and then nitrogen, and then oxygen. So we can see that in the human tissue, actually, only 3% of the human tissue is actually nitrogen. Much more than that is hydrogen. So even though that per interaction, the energy or the dose deposited through neutron capture is higher than that for hydrogen, but in a human body tissue, actually we have more hydrogen than neutrons. So the main way of those deposited in human tissue is actually through hydrogen capture, capturing neutrons. How about intermediate and fast neutrons in tissue? So hydrogen, again, it's the most efficient means for energy transfer because of the largest number of atoms per mass, and the average energy transfer is the highest. So, okay, did I skip? There is one slide. Okay, probably I did not save it. Okay. What I meant by here is that if we look at for intermediate and fast neutrons, so let's go back to this equation. So here we're talking about elastic scattering. So in elastic scattering, we have hydrogen. Actually, half of the energy is transferred to a proton, to these protons. If we go, for example, to let's say carbon, or we go to nitrogen or oxygen, we see that the energy transfer per interaction is actually lower. Okay, because just the mass here, the mass for these nuclides are larger than hydrogen. So hydrogen it's actually the most efficient way of transferring energy compared to the other elements in the body, because because the energy transfer is 50%. For other nuclides, is going to be low. Another thing is that in tissue, actually, okay, I had a nice table, but it seems it wasn't saved. Okay, I apologize for this. Okay, there is a table. I'm going to open the file actually from the book directly. Just give me a second. It's page 400 something. Yes, this is the table. So this is the table that I missed in the slide. Probably because I do the editing on another computer. I was synced to this computer. So anyway, this is the abundance of hydrogen, carbon, nitrogen, and oxygen in tissue. And then we look at, okay, the number of atoms per gram. Then we'll find that hydrogen actually the highest. So although the abundant percentage per mass is lowest, but now we want to see, okay, how many of these hydrogen atoms do we have in gram, per gram? Because that's what matters when we're dealing with doses. So for hydrogen, it actually has the highest abundance per gram. If we bring 1 gram of tissue and we count all the hydrogen nuclei there, then it will be 6 times 10 to the power 22 atoms per gram of tissue. Now, carbon, nitrogen, and oxygen, they have a lower, actually, number of atoms or abundance per gram in tissue. So nitrogen, it's only about 2%. And sorry, this is relative to hydrogen. So hydrogen is 1. Then for nitrogen, we have, it's about 2% of the number of hydrogen. So if we had 100 hydrogen molecules, atoms, then in the same mass, we will have only 2 actually nitrogen. So although for this we get a higher energy transfer, but because of their dose, their number is much lower than hydrogen. This is talking about the capture part. So even for those for thermal neutrons, although we get higher energy transferred through neutron capture, but because their number is lower, much lower than that for hydrogen, then hydrogen is really the dominant interaction, when it comes to dosimetry. And this table is in particular is for the scattering interactions. So for scattering, we get 50% of the energy of the neutron energy is transferred actually when this happens with hydrogen. For nitrogen, only 12% of the neutron energy is transferred to charged particles. So this is what I meant by this statement is that. So let's go back. The 2 important interactions: thermal neutrons. So although that the energy transfer per neutron or is actually higher when we have a neutron captured by nitrogen compared to a neutron captured by neutron captured by nitrogen compared to a neutron captured by hydrogen, because and it has even a higher cross section. So the cross section is higher. The energy transfer is 0.63. Here we have a lower cross section, but because in tissue, in 1 gram of tissue, we have much more. It's about 40 times more or 45 times more hydrogen than nitrogen. This is still the important dosimetry, or sort of the important action interaction in tissue for thermal neutrons. Now, the same thing for intermediate and fast neutrons. We still, so hydrogen is actually the most efficient way of energy being transferred. There are two reasons. First, that the number of hydrogen atoms per gram is higher than that for let's say, for oxygen, for nitrogen, and so on. And on top of that, the average energy transfer is actually the highest when this happens with hydrogen. So I want to come back. This will be probably my last slide today for boron neutron captures. It's a very exciting and very promising technology, but there are a few difficulties that probably is preventing it from actually being implemented in external beam radiotherapy. So this is the basic interaction. We have boron 10 capturing thermal neutrons. So these are thermal neutrons. And then we get lithium-7 plus an alpha particle plus some energy. This is the Q values, 2.79 MeV. This energy, part of it, about 0.84 MeV, will be taken by lithium. Lithium is not that different than alpha. So lithium, I think Z is 3, alpha is 2. So very comparable. That's why it is going to actually take a non-negligible amount of energy. And for the alpha particle, this is going to carry about 1.47 MeV. And I think lithium also is an ion, if I'm not mistaken. I'm thinking about this today because we still need to balance the number of electrons there. So for alpha, there are no electrons. So I think we are going to have 2 additional. So this would be +2, I think. Boron, or it's an ion, it's not +2 because we need to look at the Z. Z here is, I think, well, I'm getting confused. But anyway, I think this is going to be an ion. So lithium will also have, will do some damage actually in tissue, in addition to the alpha particle. But there are some problems with this technology that limits actually using it in radiotherapy everywhere. So first of all, it's very difficult to concentrate boron 10 in the tumor. How are we going to tell boron 10? We inject the patient with boron 10 and we want the boron 10 to go just to the tumor. If it went to the healthy tissue, then we're not gaining anything because again, that interaction, that neutron capture is going to happen in the healthy tissue and it's going to damage the healthy tissue. So we want to find a way to focus or to concentrate boron 10 into the tumor. And I think this is a big difficulty that, for this technology. Another thing is that the fluence rates, that if we want to conduct radiotherapy and we want to, of course, treat the patient in a reasonable time, then we need to actually have a fluence rate, okay? That is, reasonable so that the treatment doesn't take a long time. However, to get these sufficient, high fluence rates, it's very difficult to obtain for thermal neutrons. These can only be done or be obtained in nuclear reactors. The nuclear reactors that are even higher than this, I think they go up to 10 to the power 14 or even more. This should be centimeters squared. Okay. No, it is per centimeter squared. This is correct. It's nuclear. So only in nuclear reactors where we can get a sufficient, high fluence rate in order to make radiotherapy with boron neutron capture, practical. We cannot keep the patient for 1 day and then just for a single fraction. And of course, these reactors, they are, facilities. Usually, they're not, close to a, hospital in a radiotherapy facility. So that's also another limitation, getting sufficient high fluences. Another problem is that thermal neutrons, though, they do have actually a poor penetration in tissue. So if we have a tumor that is deep and we shoot the patient with thermal neutrons, the thermal neutrons will not penetrate, will not reach. So we imagine with all of these difficulties, we got the boron inside the tumor, and imagine we had even a reactor getting a high sufficient fluence rate. To get these thermal neutrons into the deep tumor, that is also challenging because they do have very poor penetration. They be exhibiting no skin sparing. This is a big advantage of photon beams, megavoltage photon beams, is the skin sparing. But now, if we wanted to do this technology, we're not actually sparing the skin. And so ultimately, the dose is deposited very high in the skin, and then the dose rapidly, or the fluence will rapidly fall off, not reaching to this deep tumor there. So this is also another difficult. So probably this technology is suitable maybe for superficial tumors, or maybe it could be done through an intraoperative procedure where we directly shoot the neutron fluence into the target, in the tumor. And another problem is that these thermal neutrons, when they're produced, usually they will be accompanied by contaminating gamma photons. And of course, now if you want to do a proper dosimetry, we have to look into the dose from the neutrons and as well as the dose from these contaminating photons, which are not negligible. And that makes it really very, very difficult. However, this technology, I think it's a nice idea. It's very promising because ultimately, if we manage to get this technology to work properly, then we can actually spare a lot of the healthy tissue. If we imagine we can get the boron just in the tumor and focusing the neutrons into the tumor, then we're going to spare the dose to the healthy tissue, especially that in the byproducts of this, we don't have any gammas, we don't have photons, we have just charged particles. Another neutron capture radionuclide might not be suitable if we get a gamma, for example, emitted from the neutron capture. So this is I wanted to talk about, even about neutron radiotherapy with fast neutrons, but unfortunately I did not have time to cover this topic. So I apologize for this. So this is my last slide for today. And that's it. So are there any questions?
شكرا دكتور. شكرا جزيلا.
الله يسلمك.